Welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one focuses on the basic principles of mechanics, in particular on resolving. When you consider a single force applied to a particle, let's say the particle is there, then it's not necessarily at an angle which is very convenient for whatever analysis we may want to make. What we can do is consider that that force as a vector is, in terms of its magnitude anyway, a side of a right-angled triangle, one side of which is horizontal and the other side of which is vertical. Now the virtue of doing that is that the triangle rule for the sum of vectors says that that initial force F, which lies along the hypotenuse, can be replaced by two vectors which are in magnitude the same size as the sizes of the triangle and directed along them so that they follow each other around like that. Now that gives rise to the idea of resolving or use of components, because from the point of view of trigonometry in this triangle, the side's length along the bottom for the horizontal must be f cos theta and the vertical one must be f sine theta. So that means to say that we can imagine our single force F at an inconvenient angle theta replaced by two forces, one of which is horizontal and the other of which is vertical. And that, well, in fact I've said vertical and horizontal, we can use any direction, but for the moment let's think in terms of horizontal and vertical to make matters simple. You can replace a single force by two components by that process. And that's a very flexible and adaptable technique for solving problems, as we shall see. So in this particular case then, those two components will appear like that, and we can see that this diagram on the right has now essentially replaced the diagram on the left. We'll see a lot of that in what follows. So although we seem to have made matters more complicated, in fact, as we shall see, it is an important step to making matters simpler. Right, there's a second example. Now again you can see the triangle there. I needn't decorate it with right angles and arrows. You can see by simple trigonometry that that's going to give us in just the same way two components, 40 cos 25 and 40 sine 25. Here's another example. Now this time the force is vertical, so that's going to lead to a trivial component horizontally. It's just going to be horizontal. If you did it with 90 degrees as the angle, then you would come to the same conclusion using sine and cos. Here's a more complicated one where the angle is not in quite the same place, but again we can always draw a triangle as there, and the same simple analysis leads to components in the same way. If the angle is in the sighted like that and the force is in a direction quite different from the original one, we can deal with that by considering either that one of the components, as in this case the horizontal direction, is in the opposite sense, or you can keep it in the same sense and call it negative. Either way the magnitudes will come from trigonometry as before. If you've got an angle not quite where you would like it, you need to use that to work out, using what basic ideas, the angle that you do need, in this case 50 degrees, and then that will lead to components as before. And finally we can look at a practical example. Well, I say finally because there are actually going to be two of them, one more complicated than the other, but this one is where we'll start. Now we've got here a picture to help us focus on what's happening, a box on a rough surface and it's being pulled, and typically it's being pulled by a rope that's at an angle. And the angle in this case is at 30 degrees. Now the information is given in standard units, kilograms, newtons, meters per second square. When that's the case, we can use the numbers without the units on the diagram because it makes it less cluttered. So I've begun that process by showing the 40 newtons as just 40. Now another point that's important is that given that you've got interacting bodies here, at least potentially, the box and the floor, I'm going to draw a diagram for the forces which has a gap in it between the box and the floor, so that it's clear that the forces which concern me are the ones on the box, not the ones that the box exerts on the floor. So here's my diagram complete with the forces. There'll be a normal reaction from the floor on the box, and there'll be a weight on the box. If I were to show the equal and opposite reactions on the floor, there would be a downward force R, equal and opposite R, and I've also shown a friction, which is the restraining force that the floor or the carpet acts on the box. From the point of view of the carpet, that would result in an equal and opposite force to the right, and as you'd expect, if there were a carpet, you'd see a ripple developing in the carpet moving ahead of the box, which indicates that from the point of view of the carpet, the box is exerting a force to the right on the carpet. But we're interested in this case in the forces on the box, and we can see that by virtue of the gap. I've also drawn the acceleration with a different arrowhead to make clear that that's an acceleration rather than another force. Okay then, let's use components to analyse this, as well as Newton's second law. This cryptic reference is to Newton's second law, and the arrow indicates horizontal resolution and the other arrow indicates vertical resolution. So if we resolve horizontally in this case, we go around the diagram looking at each force in turn. There are 4 of them. Start with the 40. If we're taking horizontal components, it will be 40 cos 30. If that's not clear, then you should think in terms of that little diagram with the 40 and the two sides of a right angle triangle with the 30 degrees here, in which case it will be obvious from elementary trig that this is 40 sine 30, for example, and the other one is 40 cos 30. It's the other one that I'm using in this case. So that's the 40. Now what about the R? That has no horizontal component, so we can skip that. The F has a horizontal component but no vertical component, and it's to the left, so hence minus F. And now the 25G, well, that contributes nothing because it's downwards. So that must equal the effective force that is on the horizontal must equal the corresponding component of mass times acceleration. So we have 25 times 0.1, because that's the component of acceleration in the horizontal direction. Now, corresponding to that, there'll be a vertical resolution, again going around the diagram. If we start with the 40, there'll be 40 sine 30 this time. And there'll be an R upwards. There won't be anything from the F, and the 25G will be downwards. And that will equal the mass times the acceleration component vertically. Well, there isn't one, so that's just 0. Now the question asks us to find the friction and the reaction forces. By resolving horizontally and vertically, we've ended up with 2 simultaneous equations which are particularly easy to solve, because the first one just gives us F equals by rearrangement, and the second one likewise gives R equals by rearrangement. So in this case, resolving vertically and horizontally is the trick to get a simple answer. If we used any other directions, then it would have been more complicated. So there's the analysis, the 2 equations that I derived. If you rearrange the F, then the numbers work out to be 32.1, and in the R case, the numbers work out to be 2.25, using G as 9.8. So finally, we answer, having missed all the units out, we can answer the question in context. Going right back to the question, our answer should make perfect sense. The friction force is 32.1 newtons and the reaction is 225 newtons, just by use of a calculator on those 2 equations. Now let's look at a more complicated situation where a box is being pulled up a hill. Now here, the selection of directions to resolve is quite critical in terms of making a problem easier or harder to solve. Again, I'm going to draw a force diagram with a gap. So here goes. We got the reaction force vertically to the, or not vertically, it's at right angles to the surface this time, and the friction force is tangential to it. The 20 is shown as before, inclined at 30 degrees to the slope, and the 10 degrees, which gives us the angle of slope, if you think round the various angles, will tell you that this one is 80 degrees, and so the one that's marked as 10 between the dotted line and the weight, that's 10 degrees. We can use either the 80 or the 10 if we want to resolve, as we'll see. Now in this case we're going to want to resolve, so the two resolution equations that we get potentially could come from resolving in any direction. I say two because you can't get any more information by taking more, but you can certainly have two. Now in this case, if we're asked to find the friction force, whereas the example we did before suggests that we would resolve horizontally and vertically, in fact in this case, if we resolve parallel to the slope, which we're certainly at liberty to do, the R force, which is also unknown, won't contribute at all because it has no component in a direction perpendicular to itself. So the thing to do here is to resolve horizontally. You could resolve parallel to the slope. You could resolve vertically and horizontally, but if you did, you'd end up with two equations, each involving F and R, and you then have to solve those equations simultaneously to find only one unknown that you want, which is F. So it's much simpler to resolve along the slope, and you should give yourself the liberty of choosing the direction which makes the problem the easiest to solve. So if we resolve on the slope, taking positive as uphill and going around the diagram as before, you've got a 20, which is at an angle of 30 degrees to the direction that you want, so it will be 20 cos 30. Again, if that's not obvious, draw a right angled triangle and look at the trig analysis. The R doesn't contribute because it's got no component perpendicular to itself. The F is in the opposite direction, and there'll also be a contribution from the 6G, not to be forgotten. So there'll be a 6G, and you can either say, we worked out this angle as 80 degrees, you can either say 6G cos 80, or you can say 6G sine 10, whichever you prefer, because they're both the same thing. And that equals the effective component of force in the direction parallel to the slope, so that must give the acceleration component, which is therefore the 6, which is the mass, times the 0.4. So you've got your F equals ma in component form shown there. Now that equation will give us F equals in one step, and so that's certainly the easiest way to get that analysis solved. So there's the equation, and I've put in the G as 9.8 as usual, and I've rearranged it on the next line simply by moving the terms around. The F comes to the right to be positive, and then the whole thing's written back to front. So if you check the terms one by one, they appear in the right place and with the right sign. Push it through the calculator, and the answer is 4.71 to 3 significant figures. Now here I've put 4.7099 ... meaning that's what my calculator shows at that point, and I've made the correction a separate step. If I need the answer for any other purpose, I can go back to that. I can even store it in one of my calculator's value cells and recall it without having to calculate it again, and it has the benefit of being a very accurate answer rather than a corrected one. So finally, to answer the question in context, the question was find the friction force. The friction force is 4.71 newtons, and that's my final answer. Ideally, a solution which has a problem to a problem should end up with a last line which makes perfect sense if you look back at the question. Well, that one does. Okay then, that brings us to the end of this video presentation on equilibrium of forces. The next in the same series is on a new topic, is on equilibrium of forces, and I hope to be with you later to explore that.